Last situation here is going to be with stretching and shrinking. And what we see is that we still have our x squared, and then in the first one we have it multiplied by 2. Notice that that's on the outside, so you have your x squared and then it's multiplied by 2. So you're looking at it like this, 2 times x squared. Over in the second one here, which I had to make a little bit smaller just to fit, notice that the 1/2 that you see there is within the squared. So it's actually being multiplied by the x before it gets squared. Now you probably understand that that's 1/2 squared times x squared, or 1/4 x squared. Okay, so I can rewrite it that way, but I do want you to see that what's actually happening is inside the thing that's being squared. So the first situation we have is the vertical stretching and shrinking. And what's happening is that when you have a number in front of your parent function, it's going to stretch it vertically by the factor of whatever number is there. So in this case, notice it's using the idea of c. So c, the factor, is 2. Okay, so it's a vertical stretch by a factor of 2. The way that you can think about this is simply take your parent function, multiply the y values by 2. So every y value in your points that you have on your parent function get multiplied by 2. So y values by 2. So notice we have the point 0, 0. Well, if you multiply the y value there by 2, you're still going to have 0, 0, so that doesn't change. Then we have the point 1, 1. If we change the y value by multiplying it by 2, we're going to have 1, 2, and then of course we have our symmetry here, so I'm going to have negative 1, 2 as well. When I plug in 2, and I shouldn't say plug in because I'm just going to use the transformation here, but I have the point 2, 4. So now what's going to happen is the y value is going to get multiplied by 2. So what I actually have is 2, 8. So, and I'm going to have negative 2, 8. So the negative 2, 8 is going to be a little bit easier to do just because it's a little bit out there. I had written on the other side, but it's going to be, somewhere up there. Okay. And then we just connect our values. So what you should see, kind of the idea here, is that this function is moving up, up, up quite quickly. That's what the 2 does. It makes sense because it's taking every y value and multiplying it by 2. And what that's going to do is it's going to shoot it up fast, fast, fast. That's the idea. And so that's the idea of the vertical stretch. Now, in terms of a vertical shrink, if instead I had a different number there, it's going to take those y values and it's going to make them smaller. And if the y values are smaller, then you're not going to have such large y values, and then that's going to shrink it vertically. Okay, this is what you got, everyone. Sorry. Okay, and then the last one here is the horizontal stretching and shrinking. So notice it says when you have this f of c of x, so that's inside before the actual function thing is happening. So it's going to shrink the graph by a factor of 1 over c if c is greater than 1. If c is between 0 and 1, the graph will be stretched horizontally by a factor of 1 over c. So in this case, c is 1/2 because that's the number next to the x that's going in. And then the factor is 1 over 1/2, 1 divided by 1/2, which is just 2. So this is a horizontal stretch by a factor of 2. Now in this case, what we do is we multiply the x values by that factor, by 2. So again, 0, 0 stays 0, 0. Doesn't matter what you multiply it by, it's going to stay there. But we have the point 1, 2. Now if we multiply the x values by 2, we're going to have the point 2, 1. So Horizontal stretch is usually doing, it looks like this. A horizontal shrink's going to look like this, stretch, shrink. So, and then the vertical stretch, vertical shrink. So normally we'd have the point 2, 4, but since we're multiplying the x value by 2, we're actually going to have 4, 4, which puts us right here. And then of course symmetry, negative 4, 4 puts us here. And also we'll have that negative 2, 1 by multiplying that negative 1, 1 by 2 as well. And then we just connect that. And so you can kind of see what's happening here with this horizontal stretch. So, you know, the easiest way to think about it is obviously just either a multiplication of the y values by the factor or a multiplication of the x values by the factor, depending on whether you have the vertical or the horizontal stretch or shrink. Now we're going to take a look at an example where we have more than one situation here. So notice we have a couple things happening. So we know that our parent function here is our x squared, because that's the main function that we see. Remember that you're always able, if you'd like to rewrite it. You know, if you feel like rewriting it, if you like seeing the x squared in the front there, that's fine, you can do that. Usually we work in to out. So if I were to do this, I would first say, okay, is there anything inside with the square? But I don't have anything inside with the square. The first thing that I see is the idea of I have this negative in front of the x squared. So the first thing I'm going to notice is that I should have a reflection over, and then because there's a negative on the outside, a reflection over the x-axis. So I'm going to do that, but I want you to see that I'm not done. I'm just going to show you what the first step would be so that you can see that this is not our finished product. This is just the first step. So it's kind of this idea here. That's the first thing. So I'm just reflecting it over the x-axis. And then I say, what other thing do I have? And we see that the other thing that we have, and that's why I thought rewriting it might be helpful, because we see that at the end of this thing, we have a +2. And so that's telling us, if you think about which one, because we've seen quite a few today, but that's that vertical shift, because it's just that number at the end that's being added. So vertical shift of, as we can see, 2 units. And that's a positive number, so it's exactly what you'd think, 2 units up. So now I'm going to take the points that I have on here that I've already created from my flip, and I'm just going to move each point 2 units up. So I guess I'll go, well, I guess I'll keep it green. I think everyone's with me there. So I'll take every point and I'll move it 1, 2. So I'm going to have this point. I'm going to have 1, 2, this point, 1, 2, this point. So I'm just moving them up, 1, 2, and 1, 2. Okay. And as you can see, that's going to give me something that looks like this. Graph paper is obviously a helpful thing when doing these problems. So that, there we go. So the green version is our f of x that we're talking about. So this is our answer here, the green, the solid green line, because it has the 2 transformations that we're dealing with here. Done. And so this is our new function. Remember, the point is, instead of, and you can always check it, right? Like you could put in values for x and make sure that your points work. Obviously, that's always an option that you have. I just want to make sure you know that. But it is using the transformations. That was the idea, was just using transformations here instead of getting a bunch of points and seeing what they are. Okay, and the last thing from this section is just determining whether functions are even or odd. This can be helpful because, again, you might be seeing things that are symmetric to the origin or the y-axis, and that can help you get an idea of what your function should look like. So a function is even, that's how we call it. Function is even if, when you plug in negative x, you get the original function back after simplification. A function is odd if you put in negative x, same thing, but out comes the negative of your function. So negative 1 times f of x. If you can rewrite it in that way, then you have a function that is odd. If it's even, it has the symmetry to the y-axis, like an x squared. If it is odd, then it's going to have a respect to the origin. Okay, so let's take a look at some examples. All right, so we've got either odd or neither. That's what we're trying to determine, and if it has any symmetry. So notice all we want to do is we just stick in negative x wherever we see x. That's all we do. And then in order to be done with it, we do need to simplify. So we write it out, and then we just simplify and see what we get. That's the idea. So by doing this, you should be able to see that we put in negative x, out came the exact thing that we started with, and so that tells us that this function is even and therefore has symmetry with respect to the y-axis. So it has y-axis symmetry. And from the work we did today, you probably notice that this is a parabola that's just shifted down 5 units, so it's still going to have symmetry over the y-axis. Feel free to do any of these that you can. You can pause and try them and then come back and see how you did, even if you're just plugging stuff in and seeing what you get. So we're going to do the same thing for B. Notice we've got something that is cubed, so we've got negative x cubed. And we know that negative x times negative x times negative x is just a negative x cubed minus 1. Now you might be thinking, is there a chance that this is odd because you have the negative x cubed? But notice that if I pull out that negative, I get x cubed plus 1. So this is not, and that these two things, the thing in parentheses, as well as this, those are not the same because of that minus 1 and that plus 1. So this tells us that we're not getting the negative of our original function. So because of that, this function is definitely not even. We're not getting the same thing. It's also not odd because we're not getting just the negative of it. So this is neither even nor odd. Not everything is. It's nice when they are because you've got some symmetry there, but this is neither even nor odd. Okay, try h of x if you want. Plug it in, see what you get. Oops, I forgot, I gotta put it in down here too. Don't forget, anywhere where you see x, you gotta stick it in. Okay. All right, so I have negative x divided by x squared minus 1. And we can rewrite that as negative x over x squared minus 1. So understand that that's the same as just putting, I can even write it like a little more obvious if you want to see that, but this negative is just, it can just sit out here. And what that means is it's basically like saying negative 1 times x over x squared minus 1, which tells us that it's just the negative, the complete negative of our original function, which makes it odd and therefore has symmetry with respect to the origin. So origin symmetry. Okay. And then our last one here is this exciting j of x. So I'm going to put in negative x there. I get this over, put a negative in there. Okay. So we've got an absolute value in that denominator, but we have negative 2x over the absolute value of x. But understand that the absolute value of x is the same as the absolute value of negative x. They're equivalent because they're always going to give you that positive version when you take the absolute value. So we can actually pull out that negative that comes from the top, just kind of put that out there, and then we have 2x over the absolute value of x, so a negative in the front of that. And what that tells us again is because we can just write it as a negative of this thing that we started with, that this is also an odd function and has the origin symmetry. And then what I'll do is I'll show you the graphs of these just so that you can see that symmetry happening. So let's take a minute and look at some of these even and odd graphs that we just found algebraically, whether they were even or odd or neither. So the first one is probably the most straightforward. We have x squared minus 5. When we put in negative x for x, we come out with the same thing. And as you can see, that's a parabola. It has symmetry over the y-axis because it is an even function. For b, we had the function g of x equals x cubed minus 1. And I want you to notice that this function, we said it was not even or odd, it was neither. And that means it does not have the y-axis symmetry, it does not have origin symmetry. We can see pretty easily it doesn't have y-axis symmetry. In terms of origin symmetry, it would have to have, for example, this function has the point 2, 7 on it. If this were to have origin symmetry, it should have -2, -7. And if we go -2, -7, there's no point there. So we can see graphically as well that it is not symmetric over the origin. For c, we said that it was odd. So it was an odd function, so it will have that origin symmetry. So notice, it might be harder for me to find some points here, but for example, we have this point here. Maybe it's like, I don't know, 1.7, comma 1. So we should have -1.7, comma -1. And you can see that we do have that point. We also have, for example, say, I don't know, 0.7, -1. 0.7, -1. So we should have -0.7, +1. We have that. So notice that the sign is flipped for both the x and y values. And so this function, graphically we can see, is symmetric over the origin because it is an odd function. And then the last one is this kind of weird function here, which has to do with absolute value. And basically what's happening is it's, as you put in a value for x, it's getting divided by itself and then multiplied by 2. It's getting divided by the positive version of whatever it is because of the absolute value. But you will see that it is symmetric over the origin because we have the point 1, 2. We also have the point -1, -2. We have the point 3, 2. We have the point -3, -2. So it does follow the idea of being symmetric over the origin and having the opposite signs of both coordinates as another point. That's section 2.6.